Let's take a look at the vertical spring situation again. So I have a spring that hangs down some natural length. And so we'll call this equilibrium 1. I add a mass to it, so it stretches down even farther, so some distance y1. And then, so this is equilibrium 2. And then I have a non-equilibrium position by taking the spring, stretching down even more, and then letting go. So this thing is going to start to move. So not equilibrium. And so this distance here is y2. Actually, no, we'll change it. We'll make y2 to there. Because there are only two forces acting on this mass, there's the force from the spring and the force due to gravity. They're both conservative, so energy is conserved. So the energy at any place in here has to equal whatever I start with. Well, I have two types of kinetic energy. Okay, final plus U final. And my initial and kinetic energy, well, we'll do that in a second. There are two types of potential energy involved here because I have two conservative forces. So I have the gravitational potential energy, and I have the spring potential energy, equals K final plus UG final plus US final. Now we do the formulas. Formula for kinetic energy is, I will assume, again, another enthusiastic 1/2 mv squared. The formula for gravitational potential energy, mgh initial, and for the spring, 1/2 k x initial squared equals 1/2 mv final squared plus mgh final plus 1/2 kx final squared. Now this is just generic. This is true for almost anything involving a spring and gravitational force and no non-conservative work being done. We can simplify it a little bit here. We can get rid of some things. I know that when I first let go of it, this is 0. I need to establish where h is equal to 0, so I'm going to let h equal 0 here. And so what we end up with here is mg negative y2, because we are moved down and y2 is a number, plus 1/2 k times y1 plus y2 squared, because that's how far the spring has been stretched from its original position, equals 1/2 mv final squared plus mg. Now we don't know exactly where it is, so we will just pick some value. So some value from here, we'll just say is some y. So mg negative y plus 1/2 k times y1 plus y squared. Now if y, I have y as a positive number going in this direction right here. So if y were up here, y would be a negative number, and I'd have y1 minus whatever that value is, or actually plus the negative. So y is just where the maximum speed occurs, because ultimately that's what I'm trying to figure out, is where is the maximum speed. Now we can take it one step further. I know at this, from this position right here, that ky1 is equal to mg. Substituting mg of ky, so I have negative ky1 y2 plus 1/2 k y1 squared plus 2y1 y2 plus y2 squared equals 1/2 mv squared. Since I'm making it generic, may as well make that generic as well, minus ky1y plus 1/2 k y1 squared plus 2y1y plus y2 squared. Let's do some distributing here. So I have negative k y1 y2 plus 1/2 k y1 squared plus k y1 y2 plus 1/2 k y2 squared, distributing there, there, and there, equals 1/2 mv squared minus k y2y. Let's make sure I have the correct one there. That is K1 there. So that's Y1. That's a Y1. Plus, and then distributing 1/2 KY1 squared plus KY1Y. That's not Y2, that's just plain old Y. Plus 1/2 KY squared. Let's get rid of what we can. So I have that term and that term cancel out. I have a 1/2 KY1 squared here and there, so those cancel out. And so what I'm left with here is 1/2 KY2 squared equals 1/2 MV squared minus KY1Y plus KY1Y. Oh, those cancel out. Plus 1/2 KY squared. Since I'm solving for speed here, I'm bringing this over to the other side, so I have 1/2 KY2 squared minus 1/2 KY squared equals 1/2 MV squared. And we can simplify that. The 1/2s can all cancel out. And so I have MV squared is equal to KY2 squared minus Y1 squared. Minus Y squared. So already all the Y1 terms have dropped out, so this gives a hint that we'll end up in the same conclusion we had before when we were dealing with just the force. So V squared is equal to K over M Y2 squared minus Y squared. That is omega, so V is equal to the square root of omega Y2 squared minus Y squared. So this is the speed at some position Y. If we want to figure out where does the maximum speed occur, well, already we see that the speed is not dependent upon Y1. The speed is not dependent upon how far this mass stretches from here. I know that dv dt is equal to acceleration. So, and also if I'm trying to figure out where this is at a maximum, I'm taking the derivative with respect to time. So that would be equal to, well, I'm going to put this into exponential form. So omega Y2 squared minus Y squared to the 1/2. So I get 1/2 omega Y2 squared minus Y squared times to the negative 1/2 times the derivative of what's inside here, which would be, well, that's a constant. That's how far I pulled it down. That's my amplitude. Negative omega 2y dy dt. That's omega Y2 squared minus omega Y squared to the 1/2. So it's 1/2 times that. Subtract 1 from that to negative 1/2. Then derivative of this be negative 2y and then dy dt. Yeah. Dy dt, that's just the change in position over change in time. That is my speed right there. So I now have this equal to, on the denominator, I have 2 times the square root of omega Y2 squared minus Y squared. And in the numerator, I have negative omega 2y v. And so this equals 0 when the speed is 0, and that actually will end up being a minimum speed. Or we take the point when y is equal to 0. So this equals 0 when v equals 0, or when y equals 0. If v equals 0, this is actually when at a minimum speed. When y equals 0, that is the maximum speed. You can go through the calculus and convince yourself. But y is equal to 0. Remember, y is defined as the distance from this equilibrium position. So yet, once again, we can treat this as same as a horizontal spring. We can just drop out the gravitational potential and have solved it with that as the equilibrium. So if you solve with this as your equilibrium position and stretching this from here, you have to bring in the gravitational potential. If you treat it from here, then you can drop out the gravitational potential. And that is the conclusion there.